Hello and welcome to Chapter 1, Section 4, the second half of our States of Matter talk. We started talking earlier today about the different states of matter, solid, liquid, and gas, and what that looks like on a molecular level. We're going to look at gas a little more extensively now. We're going to look at some of the different ways that gas can behave. Gas is always moving. It's always hitting the sides of whatever container it's in and bouncing off. It's always pushing. So if you picture the four walls, the ceiling, the floor of the room that you're in as the inside of a cube of sorts or some kind of a box, then the air molecules that are inside this room are always bouncing off of things, off of the walls, off of you, off of your computer screen, off of whatever. They're always bouncing. This bouncing applies pressure to the container. It's always pushing it a little bit out. It's always pushing you a little bit in. That's air pressure. We started talking about air pressure in the 6th grade as far as the weight of all of the air molecules on top of you, but those air molecules are always bouncing around. When you blow up a balloon or a tire, you can actually see this. You're pushing more air molecules in and they're bouncing off the sides of that container, and you move the container outwards. Now it's a little more difficult to move the walls of your room because they're pretty strong, but things made of rubber, you can move them a little bit, and as you blow them up, they can get bigger and bigger, and you can actually see this happening. Now what happens if we mess with that? Because that's what we like to do, is mess with things. So the first way, there's 3 ways we're going to mess with this, and the first one is called Boyle's Law. Boyle's Law, named after some random guy named Boyle, states that if you increase the pressure on the container, the gas volume gets smaller. If you increase the pressure on the container, so I want you to picture trolls on the outside of this room that you're in, and they're pushing on the walls, and they're pushing them in towards you. And so now you're in some kind of medieval death trap where the walls are getting smaller and smaller and about to crush you. So these being hermetically sealed trolls, let's say that none of the air that's in the room is escaping. The walls are getting smaller, so your container is getting smaller. You're increasing the pressure on the container. But none of the gas is escaping. That means that the volume of the gas is getting smaller. You can actually squish gas. You can make it so that it's still bouncing, but it can't bounce as far. Now this means if it can't bounce as far, it's going to bounce a little harder. And that's the increased pressure. It's pushing out. Picture a balloon. Have you ever tried to squish a balloon that is tied? You're increasing the pressure, and what happens is it actually pushes harder on other parts of the wall that you're not pushing on, and it squishes out. So here's the official picture of that. This first one, it's only got a little bit of pressure, but as you can see, as we continue, we're adding more and more weight to the top. We're pushing down harder and harder, which means all of the molecules inside, they still want to bounce, but they have to bounce closer together. You have increased the pressure on the inside. That's Boyle's Law. If you increase the pressure of the container, the gas's pressure will increase. Now, then we've got Charles's Law. And Charles's Law says that if you increase the temperature of the gas, it will increase the volume. Now think about this. If you increase the temperature, what's going to happen to all of those atoms that are vibrating? If you give them more energy, they're going to vibrate faster. They're going to bounce more, and they're going to hit the walls of their container harder. They're going to push out harder. So increasing the heat gives it more energy. More energy means that it bounces off the walls more, and it bounces off them harder. And this makes it want to occupy a bigger space. So if there's nothing, there's no weight saying how big this has to be, if you have one that's cold and then you increase the temperature, it's going to bounce more. That gas is going to expand, and it's going to increase the pressure on the outside, and it's going to push the walls out further. Make sense? Now we have a third law, and that law doesn't have a name. It's the unnamed law. You can name it if you want, but the unnamed law talks about this temperature in this space. If we increase the temperature in the space, but we don't let it expand, what happens? We've made them bounce farther and harder, but we're not giving them an extra space, which means we're increasing the pressure. So it's pushing harder, trying to escape its area. If you just make it hotter, it will want to bounce more. But it's trapped in a box that doesn't get any bigger, so it just pushes harder on the walls. That's increased pressure. So you can see here, this side is nice and happy, little bouncing off the walls, whatever. But over here, it's agitated. It's bouncing harder. It wants out. And as soon as it can break through one of these sides, all of that air is going to escape. Whereas the low pressure, it's no big deal. You rip a hole in the side, it's no big deal. Now, with almost everything, if you increase the temperature, you increase the size. Because as molecules get more energy, they vibrate more, and so they take up a bigger space. And that happens in almost everything, except, ta-da, water. It doesn't happen with water. With most substances, solid particles are closer together than liquid particles, except water. Isn't that weird? Why? Well, when water becomes a solid, which means it freezes, its molecules have to line up in a very specific way. And this specific way takes up a lot of room. This is the crystal structure of water. And its crystal structure dictates that all of the ears of the Mickey Mouses have to line up. And when they line up, there's a lot of airspace in between, underneath the ears. When it's water, it can just kind of fit together however it fits together, but when it's solid, it has to line up perfectly for its particular crystal structure. This takes up a lot of room. It also means that with all of that airspace that's in there, ice is lighter weight than water, which is why ice floats. It's also why water expands when it freezes, and we get to play with that in lab. Now, that was everything. Are you ready for your test? So, your job, review all your vocabulary, because you've got a quiz coming up. You're going to review the key concepts from page 34, and I will highlight them on the next slide for you. You're going to be able to explain the key concepts in at least a paragraph. Now, 8th grade, you're chunking up your paragraphs a little bit more. I'm going to ask you not just explain this to me, but really explain how it works and why it works. And I'd like you to review the labs that we've had, because I'll ask you why they were important and what they teach you. Now, page 34. Oh, I have to get through my happy little pictures. There, are you happy? Okay, page 34. Matter has both mass and volume. Mass is kind of like weight, and volume is the space that it takes up. I need you to know the difference between an atom and a molecule and all of the parts of an atom. I need you to know the difference between a mixture, a compound, and an element. These are ideas and concepts I need you to be able to explain. I need you to know the 3 states of matter in terms of thermal energy. Explain what's happening at the molecular level in a pair.